Hey, okay, welcome, I guess, to day 2. So we're in week 1, day 2 of Physics 111, and let's look at the next chapter. As you caught on, hopefully, from this first lecture, is we start off this chapter with electricity, and then it flows into magnetism, and then some other issues. But let's just say focus on the electricity here. And so we learned about Coulomb's law yesterday. We also learned about the electric field. That was probably the most advanced and tough part of it. Hopefully you got a chance to watch my supplemental problem solving, because I did a bunch of those, and I was even saying in the lecture how it's like, oh, I forgot how tough this was. And when I started doing all those problems, I remembered, and I was glad I said that, how tough they are, because you've got to add up your vectors, and you got to then, take your piece of paper, like I kept saying, and divide it in two and do X and Y component. Now, fortunately, I think today isn't quite as challenging, but it is still new stuff. And that alone makes it challenging here. So let's talk here. Let me begin this way. Let me put here on the board the title here, which is the electric potential and the electric potential energy. And I just want to pause here, right here at the beginning, and point out that these are two different concepts, and they sound so much the same. In fact, sometimes we even get lazy and don't say the whole word. We just say potential, and one is called electric potential. Please don't confuse it with electric potential energy. They are very easy to confuse, because you can see that one is an energy and the other one is something new, something that we got to talk about, electric potential. But there's a direct connection between electric potential and electric potential energy, and that's why they're easy to confuse. In addition, because they have the word electric potential, sometimes we get lazy and just go potential. Well, okay, do you mean potential energy or do you mean potential? I mean, if we throw away the word electrical on both cases, that's okay. But if we drop the word energy and just say potential, that is easily going to be confused here. So I will try my best to make sure that I always say electric potential or electric potential energy. At least definitely during this chapter. Now as we move forward, maybe I'll get a little more lazy, like is common, and just say potential, and hopefully by the contents of the conversation, if I was talking about electric potential or electric potential energy. All right, well, with that said, let me do a little review. Let me go back to last semester and say we learned, starting at the very beginning of the course, and I guess this was like chapters 1, 2, and 3, that there is a connection between position and velocity. We said if you know position, you can take its derivative and get velocity, or if you know velocity, you can take the antiderivative and get its position. So that was one option. Another option is, of course, or I shouldn't say another option, but another piece of this puzzle that we learned is going from velocity to acceleration. That is, if you took the derivative of velocity, you'd get acceleration. If you integrated acceleration, you'd get velocity. And I had those little symbols up there. I'm just going to get rid of those little symbols with integrals, because there's just something else I want to focus on. Then, if you recall, we went from these first few chapters, which was chapters 1, 2, and 3, and then we got into chapters 4, 5, and 6, and those were Newton's laws of motion. And in Newton's laws of motion, we had this thing called a net force. And the net force you got by adding up all the individual forces. And so we had things like a force from a spring, we had the force of gravity, we had the normal force, we had like a rope tied to it, so we had tension. So all of those we added up to get the, what I'll call the combined or the net force on the object. Then using Newton's second law, we divided by mass to get the acceleration, then we integrated to get velocity, then we integrate that to get position. So this is all of our mechanics. This little diagram is hopefully representing what we did in chapters 1 through 6 in Physics 110. Then if you remember, when we got into chapters 7, and, well, mostly 7, but somewhat to 8 when we got into momentum, is we said that there was an alternative approach to get to velocity. We learned about kinetic energy. We said something like this. Let me put it over here. We said the work is equal to the integral of force and some distance. And then, of course, we substituted in this MA, and then we got this 1/2 mv squared minus 1/2 mv squared, where we would integrate from some initial speed to some final speed. Now again, let me not go too far back into last semester, but I want to set up what I want to explain here today, and this diagram hopefully is going to help here with today, because we did this principle of conservation of energy. And what we could do is something like this. We could come over here and say the initial energy is equal to the final energy. And as we did all these integrals, you might recall me saying that I've got some good news and some bad news in this chapter. The bad news is there's a lot of integrals. The good news is I will do them all with you. And we got energies like this. We had one of the energies was mgy initial. We called that the gravitational potential energy. Another energy we had was 1/2 kx squared initial. And that was the elastic energy. Come on in. We had some other energies in here, but without, again, diving too deep into last semester, let me just point out, oh, and I guess I should have had the initial kinetic energy. Then we set it equal to the final kinetic energy, the final gravitational potential energy, and the final elastic energy. And a lot of times we had just one term and maybe like one potential energy and one kinetic energy. In fact, that's kind of how I want to start this chapter, is by saying that if you rearrange this, and maybe you call all of these the potential energy. So I'll say this is the initial potential energy. It involves gravity and our springs. And then over here, if we call this then final potential energy, what we could do is group the kinetic energies with the potential energies. So let me group these two together and call this the change in kinetic energy. So if I were to move this over to this side, I would have the change in kinetic energy. And if I bring this to this side, we would have the negative of the change in potential energy. And so I'll just circle that. And like I said, I got so much to tell you today that I don't want to spend too much time reviewing Physics 110, but I think it's real important that we spend just a moment to re-remind ourselves of what we did in Physics 110. And we did this principle of conservation of energy. And if you remember, then we did an integral of every force, and that's what I'm getting at. Today we have a new force, or at least this semester we have a new force. This new force is the electrical force. And so what we're going to add to our diagram is up here with the energies. This is the goal here. See where I said electric potential energy? What I'm trying to say here is we can talk about the change in the potential energy, and we'll call it electrical potential energy. that's kind of the highlights. And it really kind of sums up the whole chapter here at the beginning. In fact, this gives me a chance to say it for the first time this semester. Physics is about knowing how to apply a few but powerful fundamental concepts to explain a universal phenomenon. And so we are going to take this same idea. And that's why I keep coming back to this chart. That's why I wanted to start with this chart. Because you already know this chart. I would just say that this semester we're kind of doing the same thing, except our forces are now electrical instead of either elastic or gravitational. And our energy is going to be electrical potential energy. But we will still have kinetic energy and we'll still have gravitational potential energy. So we just have to add that to the mix. In fact, let me start with I believe this is figure 2. Your author starts off exactly the same way I'm trying to start off here. And he shows this little diagram. He says, okay, remember we're back with our conservation of energy. Remember that if you had, and you get this little mass M up on a hill, and it rolls down the hill, and he said there would be a change in the gravitational potential energy. The object would lose gravitational potential energy. And because of the principle of conservation of energy, it must go somewhere. Where does it go? And of course, he says it would go then to kinetic energy. And so you know from last semester, or actually you know this even before last semester, that a ball rolling down the hill then goes faster and faster and faster because it loses gravitational potential energy and gains kinetic energy. And so this little equation right here, where the change in gravitational potential energy equals negative of the change in kinetic energy, that's what I have right here. Although I guess my negative is on this side of the equation instead of the other side of the equation. But mathematically, it's the same thing. And so we lost gravitational potential energy. So coming back to this figure, here's what we're going to now say, is we're going to say that if you have a charge, and the charge is a positive charge, and the charge moves along with the field, and so these blue lines are the field, and so that would be the equivalent, he's trying to say, as moving along with the gravity pulling it down, it's going to be losing gravitational potential energy. And so as this charge moves across, it loses electrical energy and gains kinetic energy. And that's not a surprise, because if you think about it in terms of forces, and you put last lecture in here, you would say that, hey, this is a positive charge, and a positive charge is pushed away from a positive plate. And it's being attracted to this negative plate. And so this thing's going to go faster, 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 faster. And it will either A, hit the plate, or in this diagram, they've given a little gap so it goes shooting through. And so it's a little electrical impulse. And it goes shooting out here. And that's, like I said, where I want to begin this chapter. And that is, you're going to see me do a lot of energy considerations. And so besides the new stuff, we'll incorporate this with the old stuff. And so it does deserve a little bit of time to pause and look at the old stuff. And remind you what you've already know, just in case you've forgotten, because it has been a while. Although I will say that is the one benefit of summer school. You can go back and say, oh yeah, we did this just 4 weeks ago. It wasn't like it was a whole year ago, but it was just four weeks ago when we were back in this. And so time-wise, that makes sense. All right, so here's what I want to do. I want to come back to this chart and say, I'm going to change colors, and say, all right, now, if this chart was being applied to last semester, in other words, last semester we could have done this. If a ball rolls down a hill, and you want to know the speed at the bottom of the hill, you could have looked at all the forces on the ball, from that got the acceleration, and from that got the speed at the bottom of the hill. Or you could have looked at the energies associated with that ball, the gravitational potential energies, the kinetic energies, and then you could get the velocity at the bottom of the hill. So those were our two options. Those were our two possibilities. Now, what have we done this semester? Well, I would say that what we've done different, what we've done different in chapter 18 is really right here. We're not adding up oh, you know what? I don't want to erase it because I want to compare. Okay. We're not adding up actual forces. What we're doing is adding up electrical fields. And so if you've been struggling along with the homework, and like I said, if you watch that supplemental one I did, you'll see that to find the force on a charged particle, I put Q times the net electric field. And so I added up the electrical fields first, then used that to find the force. And most of our problems we stopped right there because it's kind of assumed you would know how to do the rest of this circuit. But I think the last one I did asked you to do a bunch of velocities. And so I had to do this step and this step and then this step and then this step, and it was like a projectile motion one. And so never forget that these other steps are still there, because every once in a while you'll be asked to continue with those steps. But I'm going to put chapter 18 right here. To put it another way, is our chapter 18, working with electrical fields, getting the electrical force, was identical to what we did in chapter 4. In chapter 4, we learned how to get the net force so that we can then continue on this chain. So chapter 18, we learned how to get the net force by first getting the fields. And then we can continue down this chain. Because just like we went from chapters 4, 5, and 6 right here, and then we did 7, we're going to do the same thing. I'm going to introduce you to another energy term. That energy term would be the electrical potential energy. And so over here in my chart, I'm going to have a new term. I'll call it potential energy sub E. And there, of course, would be initial, but there'd be some initial electrical potential energy. And over here, then there would be a new term, potential energy, and I'll say E for electrical and F for final. And so again, we're going to play the same game. And so it's important, I keep saying it, that you go back, at least mentally, and say, okay, what did we do with our mechanics, okay? And so this is our discussion. Now, here's where it gets kind of interesting. See how chapter 18 kind of had an additional step? It's a simple step, I agree. But we didn't really add up the forces. What we did is added up the fields. Now, the advantage of that is once you got the fields added up, you would just multiply by Q to get the force. Now, and by the way, in case you're wondering, is this extra step needed? I mean, why couldn't we have just added up the forces? And you could have, however, there is something very different about electrical forces compared to the gravitational forces. Gravitational forces, they always attracted each other. But electrical forces, they would attract or repel. So you were better off to not pay attention to whether it's attracted or repelling, because when you deal with the electric fields, you're not even focused on what that other charge is. And so that's the real advantage. And so we focused on the electric fields. Then we multiplied the charge, and that could be a positive or a negative. And so the direction of the force then was dictated by what charge you put there. You could either have an attraction or repulsion. So that's why this kind of additional step is really needed, because electrical stuff both attracts and repel, and gravity doesn't do that. Now I want to emphasize that because this is where we're going to play the same game. There's going to be an extra step. This is going to be called the electric potential. And so what we'll do is not focus so much on the energy at first. We'll focus on the electric potential. Then it'll be an easy step to get to the electric potential energy, and then we can just use what we've learned before about the principle of conservation of energy in order to get the speed. Well, maybe now would be a good time to give you some symbols then. So for this symbol right here, electric potential, let's call this capital V. And for electric potential energy, well, let's just call it PE with a little sub E for electric potential energy. Okay? And of course that symbol I guess I've already started to use right here as I was kind of introducing what we're doing today. Because just like back here in chapter 18, where we said you can get the force by taking charge Q and multiplying it by the electric field that's created by other charges. Sometimes I like to put this, I like to say the force on charge Q is equal to that charge Q times the electric field from other Q's. And so as we talked about yesterday, if we had, say, 3 charges, and you want to know the force on this third charge, what you got to do is get the electric field from the other 2. And so it's the other 2 that put the force on the third one. So we find the electric field from the other ones at the position of number 3. Then we multiply by charge number 3, and that gives us the force of number 3. But here's what I was saying, and I'll repeat it again. I think the hard step is adding up the electric fields from the other charges, because once you get that, you just have to multiply by the charge you're putting in that place to get the force. So it's an easy step to get force. It's also, divide by mass, an easy step to get acceleration. Now you have to integrate. That's not so easy. And then integrate again if you wanted to get to position, which again isn't so easy. Or if it is a constant force and a constant acceleration, then we can use those equations of kinematics for constant acceleration. Remember those list of 5. All right, now again, why do I say all that? I say all that because this leads to this important distinction that I started here today, and that is, what is the difference between the electric potential and the electric potential energy? And I would say it's exactly the same as this. In other words, the electrical potential energy is equal to the electric potential times the charge that you put there. And so, fortunately, this connection is the same as what we saw yesterday. And it, again, has its advantages and really is useful. We didn't do it with something called a gravitational potential. We only had a gravitational potential energy. It wasn't really needed because gravity always attracted. But this is really needed because we have both a retraction and a repulsion when it comes to electrical stuff. So that's why our diagram went one step bigger, if you will. So that's kind of this overarching piece of this. And unit-wise, maybe you can begin to see that if we talk about an energy, it would be in units of joules. If we're talking about a charge, it would be in units of coulomb. And so hopefully this will help answer this question. What would be the units of this new thing called the electric potential? And so maybe you can see that it would be a joule per coulomb. And so the units are a joule per coulomb. And like we've done with a lot of our units, in honor of the great scientist. Oops, I bumped my mic again. But in honor of the great scientists working in that field, we're going to say a joule per coulomb is a volt. And so that word you've probably heard of. What you may not have connected it with is that it is an electric potential. It's not an electric potential energy. Let me come over here to my demonstration table here for a second, because this is a good place to maybe pull out some batteries that you've probably been familiar with. For example, maybe you recognize this battery. This is a battery. I guess I'll ask you if you know what the voltage is. Here's a AA battery. Here's a voltage. Here's a C cell battery. Here's a D cell battery. Here's what we call a laboratory standard battery, or excuse me, here's a standard. But we often call these, besides AA and do I have a AAA? I do have a AAA. Okay, here's a AAA. Do any of you know, say, the voltage on maybe these more common ones, the D? Here? Yeah. Now, so the D is 1.5 volts. Okay. Now, this one's a little smaller. It's a C. Anybody know the voltage on this one? 1.5 volts. Here's a AA, smaller still. Anybody know the voltage? Anybody want to guess? 1.5 volts. Yeah, good guess. How about AAA? 1.5 volts. Now I'll leave this one alone for just a second.
Is that one 9?
That one's 9.
Okay.
Yeah. We'll talk about that one. But I'll even point out that this one here is also 1.5 volts. But I picked all these because I think it could come across surprising. They're not the same size, but they have the same voltage. What does that really mean? Well, it means they have the same electric potential, 1.5 volts. And what that means, and maybe it's more appropriate then to write the equation this way. The potential is then the potential energy divided by the charge. So in other words, the electric potential is a way to say how much energy do you get per each charge. This is that comparison I was trying to use yesterday with gasoline. You know, when you pull into the gas station, and I needed gas this morning, so I did, and I paid like $6.09, I think. All right, so it was a $6.09, and that is the price per gallon. I wish it was only $6.09. I wish I could have just swiped my card and go $6.09 and fill up my whole tank. But instead, it was like $85 by the time I filled up my tank. And so it is the rate, how much is it per gallon, but then multiplied by the number of gallons. And that's what I'm trying to start off by saying that's what electric potential is. It's an indication of how much energy you get per charge. That's why all of these batteries here, 1, 2, 3, 4, 5, these 5 batteries, I'm going to say they all have the same electric potential. They all have 1.5 volts, meaning for 1 coulomb of charge, you would get 1.5 joules of energy. But just like getting gas, my tank's kind of big, so by the time I filled up, it was $85. It was a lot of total energy in my car now. But the car next to me was kind of small, and that car still paid $6.09 for a gallon of gasoline. But their total was a lot less. It was like 45. I looked over. Okay, 45. Okay. But see, they got a lot fewer gallons than I did. They also got less energy than I did, right? And so that's the comparison here. And then there was a little motorcycle that pulled in. And I think their total was like $10. And so they didn't even get 2 gallons worth of gas. But they still paid $6.09 a gallon. They just didn't pay a total very much because they didn't get many gallons of gasoline. But we all paid the same price per gallon, and that's what I'm trying to say with these batteries. These batteries all have the same amount of energy per charge, but they don't have the same amount of charges in them. And this laboratory one has a lot of charge. In fact, we've even cut this one in half so we could kind of look at the chemicals inside and say, where is that charge coming from? And so well, maybe I'll just do it now, but this has carbon with a zinc here on the outside, so it's what we call a carbon-zinc battery, so that there's a reaction between the carbon and the zinc. So I guess we get zinc carbide when it's all done, and that's kind of that white powdery stuff on the sides. Here's a D cell that you can see the white powder a little better, and so this is a, oops. But here's the D cell cut in half. And again, you can see a lot of carbon, and then the zinc, or the white powder now, is the reaction. So I guess it would be zinc carbide. Oh, yeah, and out there it reacts. Anyways, so without getting into the chemistry of what's going on inside of these batteries, this is what I'm trying to say. They have that same voltage. Now, I will want to point out that that voltage then is the energy per charge, so it's not the total charge. I have to do 2 steps in order to get the total energy. I got to take the potential and then multiply by how much charge. Again, that's why I'd say this battery has a lot more energy than this battery, even though they have the same voltage. They have the same electric potential. And I might as well mention these other ones. This is what we call a standard battery. I forget the chemical that's inside here, but what's really nice is it makes exactly 1 volt. And so we can use this as a comparison. It's not really a good one to use to run anything. You wouldn't want to, run a radio or anything with it. But it's a good standard because the chemicals that are in there make exactly 1 volt. It's like 1.00000 volts. And then as you pointed out, this has 9 volts, which again, on the surface, you might go, wow, 9 volts. Compared to this D cell, that's so much more powerful. Well, no, it doesn't have more energy. It has more voltage. Again, that would like be pulling into the gas station where it was full service. I drove by that up in Montecito, and it was $8.50 a gallon. Whoa. Is that better? Well, that's what it is per gallon. But to be honest, if I only got 1 gallon, it wouldn't be that expensive. It'd only be $8.50. Of course, I wouldn't get very far with 1 gallon. But that's what's going to happen here. In fact, we've taken one of these D cell apart purposely, a couple of them apart. And this one you can kind of see the back end torn off, but they actually have inside of them a quadruple A batteries. And so these are all the standard 1.5 volts, or 1.6 if it's an alkali battery. And so the alkali chemical makes about a 1.6 or 1.55 volts. And then we just stack them together. And so if you take 1.5 and stack it together 6 times, you're going to get 9 volts. So that's how you get a lot of voltage, but you pay the price because you don't have much chemical in there. And so there's not much energy in there. And that's this whole idea that I'm trying to get at here. What is this slight difference between the potential and the electric potential energy? And so the rest of this chapter, I'll focus here on the potential. Because once we have the potential, it's an easy step to get the potential energy. And then it's an easy step to use the principle of conservation of energy to get velocity. And so that's the big picture that we have going on here. And in fact, this leads us to a great recipe of, let me show you figure 5 here. But now that we kind of know what the difference is between those two, we could look at something, say, like this. Here we have this charge. This charge is set between two parallel plates. And so let me just kind of remind you of yesterday. I didn't really prove it. It was near the end. But I said what's nice about two parallel plates is that it makes a nice uniform electric field. Now, what does that mean? Let me come all the way back to this equation. If we have a uniform electric field, meaning it has the same value, when you multiply by whatever charge you put in that field, then you're going to get a constant force. A constant force means a constant acceleration, which means we can use any of those 5 kinematic equations that were valid for constant acceleration. And so one of the most common problems we will do, because it is the easiest to do, is what if you just put a charge between two parallel plates? And so that's where we'll start here. And now we could do this problem and say, as it goes shooting across over here, what's its speed? And I would say we have 2 options for that. Come back to our little chart. Option A is to say, all right, we can take the electric field, from that get the force, from that get the acceleration, and from that get the velocity. And that's how I would have done it in chapter 18, sure. But for this chapter, chapter 19, I want to go this approach and do the energy. And so I guess I need to ask then this first question here. What would be the electric potential as it moves across? Well, let me build up to that, because I'll start off with then this little piece and say, if I were to do the principle of conservation of energy, I would say the change in the electrical potential energy, or the negative of the change, is equal to the change in the kinetic energy. All right? So let's just talk about a simple case of, let's say it starts over here and moves over to here a distance of d. All right. And so if I were to say, what is this equation for the electric potential? All right, well, again, let's go all the way back to chapter 7. Remember how we said the work was equal to the integral of force times the distance? And this is what I was saying about 30 minutes ago or so. I said, let's go back and redo those integrals. The good thing and the bad thing of chapter 7 was that, and the bad thing is we had these integrals to do. The good thing is I did them for you. We did them in class, and then we just had a set of equations. Let's do the same thing. Let's do this integral and some others, and that way you won't have to do them. You've got to remember kind of the result and how to apply them. But for a case like this, I'm going to put QE dx. Now, I guess I should have been, yeah, never mind. I was going to say a little careful with my symbolism, but other than a plus or minus, I'm going to throw this in here. But this is the work done. But notice then that this step from here to here, I replaced it with the electrical force. So this is the work electrical, right? So we're gonna hopefully solve for the energy electrical in this case. Now, let me do one more step. If we're talking about this little charge Q that moves across, since it doesn't change, why don't I take the Q out of the integral? It's a constant. Let me also divide it. And so work divided by Q is the integral of E dx. Wait. Now maybe you see why I did that. Isn't that this right here? Isn't the work, or I should say the potential energy divided by Q, equal to that integral? Now, I guess technically the work is this side, so if I throw in a negative, I have the potential energy over Q, and that is the voltage. Aha. Okay. Now you can see where I'm going. Oh, let me change it to a transition. Let me go from position 0 to position D. That would really mean I am doing a change in the potential to get a change in the potential energy. And that is where I'm headed. Right? How do I get the equation for the change in the potential? Maybe I'll come back to my diagram. Because if I have the equation for the change in the potential, I can then get the change in potential energy, and from the change in potential energy, I can get the change in kinetic energy, which can give me the speed. That's kind of my chain of events here. But the big thing I wanted you to see is this integral. Because we'll do this twice. We'll do it first for this parallel plate, and then we'll do it for a point charge. But if you just integrate the electric field, you're going to get the potential. And doesn't that make sense? Wait, come back over here to this chart. Before we started this semester, we said if you integrated the force, you got the energy. One step back is dividing by Q. So if you integrate the electric field, you would get the electric potential. Because force divided by Q is the electric field, and also electrical potential energy divided by Q is electric potential. Okay? And so that's how the two are connected together. So our end result here is that I would have something that looks like this. Minus E times the integral from 0 to D dx. And I pulled out the E because, again, the easiest case is, what can we say about the electric field between two parallel plates? It's a constant. And so I'm going to get just simply E times D. In fact, that was such a simple integral, maybe I should have left that one for you guys to do, right? It's just a very simple integral of dx is just x. So I guess the intermediate step was minus E and then x evaluated from 0 to D. And so our first equation, and a very useful equation, is to say that when something is between two parallel plates and you want to know the change in the potential, it is minus E times D. So as this little charge goes from here to here, I would say the change in the potential is minus E D. And so that's our first equation. And so maybe now I can get rid of this chart over here on the side and say, all right, one of the pieces to remember, in fact, I can just put it way over here, is that the change in the potential is minus ED. But please remember, this is only for this set of parallel plates. That's the big conclusion. Now, maybe I should put the more general conclusion that we've already talked about, and that is the fact that the change in the potential multiplied by Q is the change in potential energy. That was a big one. And the other one is that negative, the change in electrical potential energy, is the change in kinetic energy. And so those are the two big pieces. And I would say these second two were the general ones that I have been talking about for the last 45 minutes or so. And it's this one that is very specific to this scenario of a parallel plate. And so if somebody were to ask me, hey, what's the speed of this charged particle, when it leaves plate A and goes to plate B, I guess I would say it is something like this. I would say, all right, as it leaves plate A and goes to B, I would say the change in potential from A to B is then equal to negative the electric field times the distance. And then I would say the change in potential energy then, which is Q times the change in potential from A to B, would then be a negative QED. And then I would take this next step and say, okay, take the negative of that and set it equal to the change in kinetic energy. So the negative of this would be just a QED, and the change in kinetic energy would be 1/2 mv final squared minus 1/2 mv initial squared. And maybe then I'll actually say that, okay, whatever speed it has where it started, so at plate A, and then it goes to plate B. In a lot of cases, we might say, well, it starts from rest over at plate A. And then, sure enough, I can get the answer to what is the speed at plate B, based upon the electric field, the distance of the plate, the charge, the mass of the object, and then we can get the speed at point B. And so that's why I keep saying what we're doing today really is a match of what we did in the past. It's just now our forces are electrical and our energies are electrical. That's the only upgrade. And it'll look like perhaps we're doing a lot because we're doing the conservation of energy, but again, hopefully that's what you remember really well from last semester here. In fact, since a lot of the things we work with, these little tiny charged particles, are very small. And because they're small, they don't have much mass. And because they don't have much mass, they go very fast, and they really have very little energy. So let's give you a new unit for energy, because you're very familiar with joules. We've used it a lot. But a joule for a little tiny particle is a lot of energy. So because of that, we like to do this. We like to say, let's take a look at this equation right here. Oh, I guess I don't want to mess that up. I want to use that for the rest of the day here. But if I were to say the change in the energy is equal to the charge times the voltage, then a very useful convenience is to come over here and say, what if the voltage between these two plates is 1 volt? So in other words, let me take my standard battery. Imagine me hooking it up. So let's see, this is the positive plate. And so I'll connect here to here and there to there. And so the voltage between those two plates is 1 volt. And let's say the little tiny particle that's moving across is an electron. So that has a charge. Now, in coulombs, it would be 1.602 times 10 to the minus 19 coulombs. So if I did this calculation and I used the charge in coulombs and the potential, electric potential in volts, I would have 1.602 times 10 to the minus 19 times 1 volt. Now remember a little earlier, a volt is a joule per coulomb. So if you take a joule per coulomb and you multiply it by a coulomb, the coulomb's going to cancel off, and you're going to get units of joules. Okay. So 1 electron moving across these plates that are 1 volt would be this much energy in joules. But sometimes it's nice to do this. Sometimes it's nice to say, okay, the voltage is 1 volt. And the charge, instead of in coulombs, let's put the charge as charge E, where E stands for the charge of 1 electron. Okay. Now, obviously, if I just substitute the charge of 1 electron right here, I just get the same calculation. But what's nice sometimes is to leave this alone. Don't put in the actual number. Just leave it the way it is. Kind of like we do with a nano or a micro. We'll just leave it as a symbol and put it with the unit. So this would become 1 eV. We call that an electron volt. It is a unit of energy. And so this new unit of energy I'm trying to introduce you to is called an EV, 1 electron volt. And 1 electron volt is this much energy in joules. And so we have a new unit and the connection of the new unit to the old unit of energy. And so 1 electron volt is actually going to be a very convenient way of dealing with energies. And so for quite a bit throughout this semester, you'll see us doing energies in electron volts because of that. I think he even has it listed somewhere in here. He's got some examples, and they all seem to be in, maybe it's still a little early, electron volts. But I noticed in the homework problem that happens a lot. It says, what is the energy? And they want it in electron volts. Or they give it to you in electron volts. And then, of course, you got to get the speed. So you got to convert the electron volts into joules in order to finish the problem here. So this, like I said, is this whole idea of the energy. Now, I guess I'll keep going here, because also we got a nice little subtlety here if we look at this equation, and I'll erase it here because I do have it written over there. But what if I were to maybe take this right here and do the equation backwards? Here's what I mean by backwards. A moment ago, I said, could you tell me the speed of that little charge? And I used the principle of conservation of energy. And the way I did that is I said, okay, let's get the change in potential. And so I said, take the electric field multiplied by the distance, then multiply that by charge. That gives you the electric potential energy. Set that equal to the kinetic energy, and you can solve for it. A lot of times, though, in practice, it's kind of the reverse. We go to build our parallel plate, and then the question is, what's the electric field? And so let me come back and study this equation also. So kind of like we did here, where we said, look, we could have some new units for energy. We can study this equation and say, if we rearrange it for the electric field, we could say the electric field would be what is the voltage divided by the distance between those plates. So, I scrolled away from my picture, but let me scroll back here. And again, let's imagine that I'm actually going to build this. And so I would come over here and I would take this 1 volt, right? And what I would do is connect this wire to here and this wire to here. In other words, what I know is the voltage and the distance. And what I'd like to maybe solve for is what's the electric field. In fact, maybe I'll even kind of imagine building it. Here is my battery. Here is my parallel plates. Now, my setup, I can't do it like this, but I can do it this way. And now I just need a little distance between them. And I do have what I'll call spacers. They're little tiny squares of plastic. And that will just make them separate slightly. It also means I got plastic, not air, but mostly I got air in there. Okay, so if you'll forgive the little piece of plastic, actually vinyl, then I'll just go ahead and say, look, I've got my parallel plate. If I hold it up this way, it'll hopefully look like that too. But if I took a couple of wires, take a couple of wires, and I put this positive one, and maybe just to match it, I'll put the positive one, well, let's see, I'll imagine picking it up like that to match up there. So I'll put the positive one at the top, and I'll put the negative one at the bottom. And I would say I now have an electric field between those two plates. Okay, and what is its value? Well, if I come over here to calculate it, I will start off by saying it's 1 volt. That's how much I've connected to the two plates. A battery of 1 volt. And then I'll divide it by the distance. Now, the distance of this vinyl piece is like 1.1 millimeters. Okay, so this is a big piece so you can see it a little better. But I'm going to put then 1.1 millimeters. And then I'm going to rearrange it or change the units. I'll grab my calculator here to get a number here. What is 1 divided by 1.1 times 10 to the negative 3? So this is 909. And the math is pretty easy, but here's the units I want you to see. What would be my units here for this electric field that's between these parallel plates? Do you see it's a volt per meter? Notice that when I said here are units, plural, for energy, I had the old one, if you will, joule, and today's new one, and obviously they have to be connected. And I'm going to say the same thing, that what then are we seeing here? We are seeing units of the electric field. And I will say, what was our old units? Now, this is kind of weird to say old. It was just yesterday we got to electric field. But yesterday, we said the units for the electric field were a Newton per Coulomb. But doing this calculation, based upon this first integral that we did, I would say that I have units of volts per meter. Now, I'll convince you those are the same, but what I want to point out is don't be surprised if sometimes we use newtons per coulomb for the electric field, and that's what we did in chapter 18 yesterday. And you guys are probably still working on those and those problems and saying, okay, and that's fine, because we thought of the electric field as the amount of force you got per unit charge. But now we can look at the electric field a little different. Now we can say the electric field is the amount of potential for each meter. So it's a rate. It's volts per meter. In fact, let me convince you here that they are the same. So let me start with volts per meter. And then let me remind you that a volt is a joule per coulomb. Let me simplify that a little bit. Oh, let me remind you that a joule is a Newton times a meter. Let me then cancel a meter. And sure enough, a volt per meter is the same as a Newton per coulomb. Yep, fair enough. And so we're going to be using newtons per coulomb, probably when we're dealing with forces, and when we're dealing with energies, we will go volts per meter. And that's why if you scroll down here, you'll see that your author uses for the electric field in this chapter volts per meter quite often. Oh, in fact, here's where he did the conversion to remind you. So 1 Newton per coulomb is the same as 1 volt per meter. So the good thing is there's not like a number you got to multiply by. It's just a change of units. But I think that does surprise students. And I wanted to make sure I pointed that out. That, okay, wait. We're going to start using volts per meter for the electric field, even though we started using newtons per coulomb. It just depends on what we're looking at here. Okay, well, let's see if I could just kind of recap. What did we do? We started this by trying to remind you of the principle of conservation of energy. And I guess here, the principle of conservation of energy. And now the only thing we added was that we have this thing called electric potential energy. And what's nice then is the electric potential is connected to the electric potential energy. And so we can actually get the potential by doing that integral. Or maybe I should have even put it on here that if you integrated from A to B, remember we had a minus the electric field times dx is the change in potential. And I actually did that integral for the parallel plate, which then led me a chance to have a discussion about a new unit of energy. It also led me for a chance to discuss a new unit for the electric field. So let's do another integral. Because like I said, to get the electric potential, we have to integrate for that situation. And the first one was the parallel plate because it was so simple. The next one is a little harder, but not too bad. Maybe I'll just show figure 8 here because your author is saying, okay, here is a point charge. What would be the potential for a point charge? And so maybe I'll fill in this little box right here. What is the change in potential for a point charge? Now, let me say it again. Here's the nice thing about that, is if we know this equation, which comes from an integral, and so if we do it now, you won't have to do it again. But if you know that, you can start right here. The change in potential gets you to the change in potential energy. The change in potential energy gets you to the change in kinetic energy. And so that's why these two are going to become really good equations, because they can then tell us what the change in potential is. It depends what we're dealing with. Are we dealing with a parallel plate or are we dealing with a point charge? Oh, all right. Well, let me come over here and do this integral. Now, to do the integral, we need to obviously go back to last chapter. And so I'm going to say, all right, what is the change in potential? And maybe I'll even put here for a point charge. If I integrate E times dx from some point A to some point B. Now, your author doesn't really have a point A and B. Like the other problem, he had plate A and plate B. So I'm going to draw this same picture. Maybe I'll think of it as maybe starting at this inner ring here, maybe this green one here, and then coming out to this last green one there. And so I'll kind of draw that picture here. So let's see, here's the point charge, and the electric field. Let's see, he draws it in blue, so I'll copy him. So blue, blue, blue. And so Remember, electric fields, can't see them with our eyes, but this is our visual way of trying to say, you know, how strong is that electric field? And then maybe I'll take a green ring, and as you'll see in a moment, everywhere on that green ring we are the same distance away, so we're going to call that the same potential. A fancy word, we'll call it an equipotential. We'll say everything has got that same potential. But let me just take a charge, or let me take a point maybe right here. And so this is R A, so I'll start at A, and I'll move out here to B. So I'll call this RB. And so let's make another circle. And I'll say it again, it seems like what would matter here is only the fact that we've moved radially outward. That's why the circle would all be the same distance away. That's why I would say the circle all has the same potential. And so, again, fancy word, we'll call those circles those equipotentials. So the green are equipotential lines. The blue is this electric field. And I want to do this integral. Like I said, so that what I can do is once I know that integral, I can then just say, okay, now I have an equation for the change in potential from a point charge. And if I use that up here, I can get the change in potential energy. And if I use that, I can get the change in kinetic energy, which could tell me how fast it's going after it was pushed away. And so maybe this is a little charge Q that gets pushed away, and the question is, how fast is it going right here? All right, so here I'm going to do this integral. So I put the minus. I guess the thing to remember, though, is what was the equation for the electric field from a point? Have you got that far? That's chapter 18. Does that look familiar? And so this is the electric field from a point that we did yesterday in chapter 18. What is that electric field? Now, in this case, I should probably change the dx to a dr, because really what that means is you integrate the electric field. So you integrate along the electric field. And in the first one I just did it along the x-axis, so that's why I did a dx. Obviously, I could have laid it the other way and done a y-axis. And in this case, we could even call this the x or the y-axis. It doesn't really matter, but I think it just looks better if I just call it an r. It kind of looks like radially outward. So you kind of realize that it would be the same equation, the same math, whether I went off at an angle or whether I did go along the x-axis or whether I went along the y-axis or maybe the negative x-axis. And then fortunately, this isn't a too hard of integral to do. I could pull out Coulomb's constant and the charge and then have an integral of dr over r squared. And again, from some a to some b. And then maybe this one is best solved by reminding you that this is just a power function, although it's a square in the denominator, so let me bring it upstairs, so it would be a -2. And these are the integrals that I said are not too hard, the only ones I would give you, but again, you're not going to have to do them. I'm going to do them here for you. And so remember, we add 1 to the exponent and divide by that new exponent. So if I add 1, I get r to the -1. And if I divide by that new exponent, that's a -1. And then I guess I can evaluate it from A to B. And so I get the change in potential from A to B. And it looks like the two negatives cancel off. Okay, that's good. I have my K and my Q. Why don't I bring the R downstairs so I don't have the negative exponent? And then I'll go from A to B. And so then I'll have KQ over R at B minus KQ R at A. And good. That's what I was looking for here. Let me put it over here in this chart here. So this is KQ over RB minus KQ over RA. Now again, let me emphasize, we derived this for a point charge. So this would only work for a point charge. That's where I'm going to put point charge. And this would only work for the set of parallel plates. So these are, not interchangeable. You got to look at what you have. And as long as we have a parallel plate, we can do this. But if we have a parallel plate, don't do this. And likewise, if we have a single point charge, we'll do this, but don't do that. Now, these are the general ones, so we can apply those to any scenario that we want. But that's the idea of this potential. Now, your author takes this a step further. Fortunately, he says you don't need to do these integrals. These would be really hard. But what would be the change in potential if you were next to two charges, what we call a dipole? One's positive and one's negative. And so maybe you could start on this green circle and then go along this electric field and get to that green circle. What would be the change in potential? Well, let me emphasize, that's getting beyond the scope of this class. I just wanted to set that up and say, notice then that there would be these things called equipotentials. They're green lines in the picture. They, of course, would have to be perpendicular to the blue lines because, again, you change voltage when you go along that blue line. So if you move sideways to the blue line, there's no force. Remember that way back in Physics 110, where work is force times distance, but it's the component of the force in the distance you move? So if you ever move perpendicular to the force, there wouldn't be any work. And so your author's trying to say that if you are, say, right here, and if you move perpendicular, so along this green line, you wouldn't change your energy level. You're not doing any work. So if you know what the electric field kind of looks like, so if you kind of know what these blue lines look like, then the green lines are all perpendicular to that. And those are our equipotentials. Well, again, maybe I shouldn't dwell too much on this because that's really then taking it a notch further than our class is going to go. But it is nice to see the electric fields. It's nice to see the equipotentials. It's nice to see how they're perpendicular. And it's nice that we don't have to do the integral. So we won't do the integral from one of those to another. We'll leave that for another class. And we'll leave that for the engineer class, have to do the integral. How about that? Oh, we can do this one too. Here is a, let's see, a bipole, because they have the same charge. But again, you can kind of see the electric field that we talked about in the last chapter, and then you can see these green lines that are drawn perpendicular, and so these are called the equipotentials, and so they're saying everywhere along, say, this green line is negative 5 volts. And everywhere along this one is negative 2. And of course, then what would be nice is if we had an electron that maybe started at 2 and went to 5, we could get the change in potential. We would go final minus initial. So we would go negative 5 minus a negative 2. And so from here to here would be a change of 3 volts. Well, let's get to one that is more appropriate for our first discussion. And this is that parallel plate, right? So the parallel plate has this nice uniform electric field. And so perpendicular to that are these green lines. And so these green lines are our equipotential. The green lines are all a certain distance from that plate. And you can even see that one in the math, because if we come over here to our equation, we said that the change in potential is the electric field times however much distance you moved from plate A. And so if I come over here and start at plate A and move a little distance, and it looks like that would be a change of 25 volts, because they're saying this is at 100 volts and we move over to 75 volts. So that would be a change of 75. But if you did that same distance anywhere from plate A, it's still the same change. And so everywhere along this line is 75. Right in the middle, doesn't surprise you that everywhere in the middle the voltage is 50, because again, you would move from here and you would go a certain distance, and that distance should be twice as much as the distance to get to the 75, because we've got kind of a linear equation, or not kind of a linear equation, it is a linear equation. That's the easiest equation we can get, just electric field times distance. And so if you double the distance, you double the change in voltage. And so from here to here was a change of 25, here and double the distance would be a change of 50. And if you triple the distance all the way out to here, it'd be 25, 25, and 25. So it'd be a change of 75. So we've gone down by 75. So we've gone from 100 down to 25. And then we can go all the way across and get all the way down to 0. Okay? And so that's this idea of this chapter. Now, with that said, your author says, okay, now that we've got this whole idea of equipotentials and potential energy and principle of conservation of energy, we can start doing some problems where we actually send the electron across and ask for its speed. We could also then start talking about storing these charges on this plate. And that's the second half of this chapter. And it's earlier than our normal break, but I think this would be a good time for a break. This would be a good time to say, okay, we're gonna shift gears and say, okay, let's talk about the total energy stored on these plates and what we might use with it. And so these are called capacitors. And that's the second half of this chapter. All right, so why don't we take our 15-minute break and come back at 9:37? All right. Hey, all right. Hey, welcome back from our break. I think it was a well-needed and well-deserved break, and actually a really good timing here, because we've been dealing with energies. And so now let's do the other half of this chapter, and maybe some examples or two if we get that far, but otherwise I'll do a supplemental again. So that being said here, let's look at the second half of this, and that has to do with capacitors. And so your author starts off with a nice picture here, and really I would say it's the same that I just built right here. I mean, we built this, and of course we were using it to understand the physics about the electric field, but now we get into something what I'll call practical, something of what are we going to do with this new information that we have. And obviously electrical stuff is all around us, so it probably doesn't take me too much examples to convince you how important electrical and mechanical features are here. But one of the simplest ones to talk about is what is called the capacitor. And so your author has a picture of it here, but capacitors are used for many different reasons, but one of the simplest reasons is they're just an energy storing device. And so I'll put here capacitor. What is a capacitor? It's a device that stores, and I'll put two things. That it stores charge, but of course that also means it has energy. In other words, what we've been building really is a capacitor. I didn't use the word capacitor, I just used parallel plate, but by hooking up this battery to the top and the bottom here, of course I made an electric field in here, but I have made one plate positive and one plate negative, and so I have separated the charges. And this is what your author's showing here. It looks like he shows one of these car batteries. Looks like 1, 2, 3, 4, 5. It looks like he's trying to show 6 cells. In fact, I should have probably showed the equivalent of a car battery. This is a motorcycle battery actually in the last section, but we chipped it away so you could see the chemical reaction, because this one we cut and you can see the carbon and the zinc. This one's a little different. It's a liquid battery, so it's got these lead plates. There's lead, lead oxide, and sulfuric acid. You know, we don't have any more acid. We chipped it off and broke it apart. But you can kind of see where the chemical reaction would take place. And that would actually give you 2 volts. So that's what's nice about lead and lead oxide, is give you 2 volts. Lithium ion's another good one, as you know. That gives you 3 volts, so better still. So, and they're much lighter. Lead's pretty dense and heavy, so carrying around a lead battery is not real nice, but a lithium ion is, and so you get a lot of energy and very light. So that being said here, this then is what is buried inside of this battery, and there's 6 of them, so they stack them together. This motorcycle battery has 3 of them. You can kind of see the 3 cells. If I tilt it, you can see where you could fill it up with the acid there, and so this would be a 6-volt motorcycle battery, because I'd get 2 volts for every cell. This would probably be, it looks like to me, a car battery. So this is the 12-volt car battery, where I have 6 of them to fill up with acid. But the battery's not real important here. What is important here is if I just take the plus terminal, and so why do we call it a plus terminal? Well, because that's the one at higher potential. And the negative one is at the lower potential. And so without getting into the exact shape of the electric field, if they were point charges, it would be this equation. If they were parallel plates, it would be this. But not worrying about the actual shape of the electric field inside of the battery, those chemicals and the movement of those charges create an electric field that if you integrated it up, it would be 12 volts or 6 volts or 1.5 volts. And so it's the chemicals inside that make the electric field. Remember, all of our materials made out of charges. So there is some electric field, and so one side is going to be lower in potential, that would be with the electric field, and the other side is going to be higher in potential, because that's with the electric field. So we'll always label our batteries then as one side is plus and one side is minus, and then we will give a number. That number is the difference between them. And the plus one means that it's at a higher potential. So if I were to grab this analogy here, I would come over here and look at the little plus and say, okay, this one is at a higher potential than this one. And so when I connect it, the higher potential, or I should say the electric field, goes from the high potential to the low potential. And so the electric field is going to go from plate A to plate B, which is why you can see your author then said negative charge. So the negative means lower potential. It also is where the negative charges would be. And so the negative is there for both reasons. Negative charges come out of the negative terminal. It's also the lower potential side. The plus is the higher potential side. And again, I'm not going to say pluses come out of there. Remember, this was a big thing about last chapter. It's going to be the lab today. That the plus is there because the negatives left. And so what would happen is this battery would suck in the negative from plate A, do its chemical reaction. You would call it a redox reaction for those of you who've gone through chemistry already. And then it would shoot out the electrons after the redox reaction. So for every one that comes in, one comes out. And so you end up with a bunch of charges on plate A, so we'll call it a positive Q, and you end up with a bunch of negatives on the other plate. So we'll call it a negative Q. And they're exactly matched. So this is going to be our stored capacitor. This is how we're going to store the energy. You might say that the total charge on the capacitor is 0. Never forget that. But there is an equal and opposite charge. And that's, again, what I have here. I've hooked up the negative right here. And so I've got a negative charge on this bottom plate. And I've hooked up the positive here. And so there's a positive charge. And if I look at the whole thing, I would say the whole charge is neutral, because there's an equal number of positives on this top plate to match the negative plates. And I just used the chemicals in here to help push them out of the battery onto the bottom plate and suck them in from the top plate. And so that's the whole idea of the chemical. And so how much charge can I store? How much energy can I store? And depending on the situation, it could be quite a bit. And I'll show you a few examples. Now, so it doesn't take up too much space. They actually then show a typical capacitor then is kind of rolled up. For us, I'll grab my box of capacitors. But this is kind of our silly way of illustrating what's going on there is we take then some kind of insulator, and then this will be my one metal plate, another insulator, and this will be my other metal plate, and then we just, I'll take this one off for a second, we just roll it up. And so that way you can get a lot of surface area and get a lot of charge in a shape that's really not very big. And so a lot of our capacitors look like these little cylinders because they're rolled up. Now, if you don't want to store much charge, then it's no problem just making, you know, like two plates and putting them together, and maybe they're the size of a dime, and so you just have two plates. Now, you're not going to get much charge there, but that certainly would be a capacitor. So I have everything from little capacitors to big ones, but most of the ones I have in here are pretty big, and they're big purposely because they're rolled up. Here's one that looks like a cylinder that's rolled up. In fact, maybe I should look at the one I already got out, ready to show you some other things. But here's a big one with lots of charge on it. Here's another one. Here's another one. And I don't think I have any ones that look anything different than a cylinder in here. I don't have any discs ones. Your author has a picture, so I'll show you the picture of one. Here's an adjustable one. Here's one of my favorite ones. Is you can then have a knob, and so you can turn it, and these little metal pieces slide in, and of course now there's multiple plates, and so this one's a bit more advanced than our simple model. That's what this was all about. If we just do, oh, I guess I needed my second plate. I shouldn't have taken that off. Okay. Not going to do any good with just one plate. Okay, so putting my plates together, this would be the capacitor. But we could also stack multiple plates, but I'm getting ahead of myself here. We'll do that in about a half hour, but this is what this one would be. Anyways, oh, hey, well, here's a good one out of an old ham radio. And so we can change it, and we'll learn later on that the tuning of the frequency is based on the size of the capacitance. So you turn it to here and you're on one frequency, you turn it to there, you're at another frequency, you turn the dial there, you're at another frequency, and so you can adjust the size of the plates that overlap and therefore adjust the capacitance of it. But again, the simple thing I just want to say is we can store charge. And your author gives you a couple pictures here just to give you an idea of a capacitor before he dives into the math. Here's where he kind of says, here's a better picture where you see the electric field once you've charged them up. Okay. Then he starts getting into the units, and so I will here in just a second. But here's a good photograph of some different ones. And the one I was thinking of is this disc-shaped one. That's, you know, probably about the size of a quarter, maybe smaller, maybe a nickel, but it's just two plates and a little material in between them so that the electrons, you know, and the plates don't touch each other, and like I did there, and so you could just kind of get the storage capacitance. In fact, what I'd like to do then is maybe show you some of these capacitors. Here is one that, again, is wrapped up, but this one is kind of on the expensive side because it is so thin. The aluminum foil, the plates, are really, really thin. So that's what makes it expensive to make. But because they're so thin, you can roll up a huge distance. Miles of distance if you do this right. And so you can get a lot of charge on here. And so that's what this first power supply is for, because I'm going to go ahead and say, what if I go ahead and hook this capacitor up, and you'll actually see my dial. Unfortunately, it looks like it's reading something really small. don't believe that. It should be 0. This is supposed to be showing how much charge is coming out of this machine. And so you'll watch when I hook this up, it gets real high at first because it's just dumping charge on here. And so it's filling it up and filling it up and filling it up. In fact, you noticed it was really high at first. And then, of course, now it's settling down because, you know, the charge is building. And so it was easy to get the first charge on there, but then the second was a little harder, and the third was a little harder and harder and harder. And so I have charged this up to 5 volts. And so I've got 5 volts, and it looks like no more, maybe a hair more charge is coming on, but now I can do this. Ha! Energy. Take it with me. Hook up a light bulb. Ta-da! And light bulb goes on. And so the charge is now coming off of here and going through my circuits here and running the light bulb. And so this goes for about 30 seconds. Maybe I'll just kind of let it peter out right here in front of us all here. But it's gotten so little now that it's still there. You can see it's still on, but it's very, very dim. But there is the idea of storing this energy. In fact, I just can't resist because that one stores a little bit of energy. I mean, obviously it ran the light for what, 30 seconds? Probably a little longer, but not well. So maybe it ran at 15 seconds well and then had very little left. So it's not like it's going to replace a battery. Of course, I would point out that that's kind of the holy grail of electrical engineering. It's like, oh, can we replace all of these batteries with just simple charged on a metal plate? Because they charge up so quickly. Could you imagine charging up your phone and just plug it in? Ding! All right, full charge. I'm good for a week. You know, it would be amazing. Or a car. But so far we haven't got that far. And so we've got lots of batteries. But this one has a lot more energy. And so maybe this one is worth looking at. And you can imagine that the amount of energy has to do, in fact, I'll give it a chance to warm up here. Yeah, I think we'll be okay. But it has to do with how much charge we put on there, which has to do with how much voltage we apply. And so for this one, I'm going to go kind of on the high side here. And instead of a baby 5 volts, how about we get like 350 volts? And so I'll make the connection. And you might even see this needle move a little bit. This is the current going on. These are the electrons. I shouldn't use the word current yet. That'll be for tomorrow. But this is how the electrons going on, and then this is the voltage of how much is actually there. So if I turn it up, you'll see it starts to fill up, and I just don't want to turn it all the way on in one big shot. Might overwhelm it. But I'll just keep slowly increasing it. And this dial, I'll read it since you probably can't see it at your distance, but that's 200 volts right there. So I'll keep going, keep going, keep going. We're at 300 volts. And I think this one maxes out about 350. Looks like 360. Unless the dial sticks. Kind of an old meter. Not 370. We'll call it 370. But there's 370. And so I've got a lot of charge. So what would happen, and this is why I got this metal rod here, if I came across and I touched the positive and the negative so that they can jump ship. So I don't know if you noticed this, but we've been really using the principle of a conductor versus an insulator. And so the negatives here want to move over here and go to these positives, but they don't have any way to flow. But if I make a conductor with this metal rod, they would gladly flow across there, right? and then they would go very fast, and they would give off their energy, and that's how we get that energy back. But in between them is an insulator. And so right now, they can't go back. So if I were to remove these, I would say I now have a lot of energy stored here. And in a minute we'll get to the math and say how much energy is that. But if I short circuit it, we'll see all that energy released. And I'll do it slowly. You might want to hold your desk, because even though I know it's coming, it still always scares me. But maybe I'll just go across the top here. Ooh. And see, always makes me jump. And it's like, you sure it's all the way off? So when I touch it, it doesn't hurt me. All right. So there can be quite a bit of energy here, and like I said, capacitors are used to store energy, to store charge, and for a lot of other reasons, and we'll build up on those for a while. But like I said, this part of the chapter is actually what I call a practical chapter, one that says, okay, what is the usefulness of this? And so, again, you might think of this a little bit like storing water in a bucket or storing gasoline in a tank. It is just a storage device. It stores both energy and charge. Okay, so with that in mind, let's define this. We will call the capacitance C. We're going to say, okay, what is the capacitance of our capacitor? And let's define it this way. How much charge do you get per voltage? So in other words, if I were to hook up 1 volt, how much charge do I get for every volt? That is what we're going to call the capacitance. Be careful with this, because again, this is one of those rate things that I think confuses students. Because if I were to ask you, we'll go back to gasoline, about a storage tank in my car, I've got a tank. And if somebody asked me how big my storage is, I would say, oh, it's 20 gallons. My tank holds 20 gallons. Well, that's the total it can store. It doesn't mean I have a total of 20, right? It just means that's the maximum that can store. That's not quite what capacitance is. Capacitance is how much charge for every volt. See, if I come over here and look at this big one, it says its capacitance is 2,200 microcoulombs per volt. So in other words, this says my capacitance is 2,200 microcoulombs per volt. And notice it's per volt. It's not the total charge in here. So when I hooked this to this big power supply and I cranked it up to 370 volts, how much charge did I have? And I want to emphasize, it was not 2,200 microcoulombs. That was the amount of charge I got for each volt. So if I were to ask how much charge was on this capacitor, I would multiply these two together. In other words, I get 2,200 microcoulombs per volt. And then how many volts did I apply to it? And so in this case, it's 370 volts. So the volts would cancel off. And I can come over here and then say 2,200 times 370 makes 814,000 microcoulombs. I suppose we might take advantage of the micro, which is 10 to the minus 6, and then just write that as 0.814 coulombs. So I'll say it again. The capacitance is a nice way of measuring how much we're storing, but it is how much per volt. And so it is not the total. It's not, again, like a 20-gallon tank where you just say, oh, you get 20 gallons, that's the total. You could have less, but no, this is not the total. This is how much you get per volt. And so that's a big idea of this plate. Now, also, and I think I mentioned this, but it's probably worth repeating, this is the charge on one plate. See, because one plate's positive and one plate's negative. The total charge is still 0. And so maybe this is better written as the magnitude of the charge on one plate. Because again, one plate's positive, one plate's negative, the total is 0. All right, well, your author then points out that, hey, let's look at this parallel plate again. This parallel plate, like here, is a nice one. And your author keeps using it because this is the uniform electric field. And in this uniform electric field, it might be asked to might be nice to ask, well, how much capacitance do we get? And your author kind of gives you a nice equation without proof, and so I'll do kind of the same thing. Your author says how much charge you can get on there per volt, in other words, what is the capacitance, would depend upon, and I think you can see some geometry factors would go in. The first one he argues is, wouldn't it be the area of the plate? How big is that plate? That's why I was saying earlier that this one here can get so much charge on it because if you unroll it, you're going to have a huge surface area. And so your author says one of the factors is the area. What is the size of that metal plate? And that makes sense. And the other factor, and of course inversely proportional, is the distance that's separating them. And so you can imagine that if they were close together, they would kind of suck in those charges and you would then be able to store up more. And so your author argues here that, okay, you'll have a bigger charge per volt if they're closer together. Now, we do have some troubles if they get too close together, because remember, one's positive and one's negative. And remember those sparks that we were doing with the Van de Graaff yesterday? And so you certainly want to have a certain enough distance between those two plates, otherwise they'll spark. And so if you're trying to get a lot of capacitance, your goal would be, number one, to get a lot of area, and then number two, to get the distance between the two plates as close as possible. However, like I said, if you get them too close, you get problems because they'll spark. That's why, again, coming to all these capacitors, this one, it really is so big because the spacing between the plates is quite a bit. And that's why it says this one is safe to apply up to 450 volts. And so they give you a limit. They say, okay, look, as long as you stay below a certain value, you won't get that little spark inside. But if you get it too much charge, which is too much voltage, you'll get a little spark, which is a trade-off, because this one here, remember I said that they made it really thin so they're really close so you can get a lot of surface area? And they did, and so they get a lot of charge on here. But they also say do not exceed 5.5 volts. And so that's the price to be paid on this. You just can't put much voltage on it because the plates will get too close together. In fact, it's kind of fun to see what might happen if we do get them too close together. And so let me use this middle power supply because I think I got this one set at about 100 volts. Okay, so we're at 109 volts and 0 charges coming out right now. Let me turn that off. And let me just grab a capacitor. I thought I had set one out here. Ah, here it is. And it's not a very big one, I see that. But it does say, well, that's bigger than I gave it credit for. It's 220 microcoulombs per volt. Okay. But it says 25 volts. So it says do not hook it up to more than 25 volts. You hook it up to more than 25 volts, and that means that your plates are so close together that they'll spark, and that will make heat. And in this case, the heat will warm the gases inside, and they've made it wrapped tight. And so the little liquid inside will start to boil, and the pressure will build, and it'll go pop, and it'll be like a little explosion here. So let's give it a try. So I'm going to go ahead, and I'll hook up the negative terminal here, and I'll hook up the positive terminal here. And I'll scoot this back so you can kind of see it. I'll also keep it a little on the low side and point it in this direction, and we'll see what happens if I don't get too close here, and it won't be nearly as big as that one. But watch what happens when I turn it on. It doesn't happen right away. You will see this number right here. And so it's actually sparking inside of there. There it goes. Scared me. And it's actually sparking inside of there. And that's because it said don't go over 25 volts. This is why. You will get those little sparks here. So anyway, so we're going to have a limit here, and there's a good and bad about that small d versus the big D. Now, there is one more factor here, and that factor really is, what do you put in between the two plates? We right now are putting what I will call free space. In other words, there is nothing between them. We refer to this as the permeability of free space, although to be quite honest, I don't have exactly free space. I have air molecules. So this right here, as I said, is a capacitor. And I know I put a few pieces of vinyl here, but if you'll forgive the vinyl as just being spacers, I would say the material that is between these two plates is air. Air is not free space because air does have molecules. Free space is no molecules. So if there was no molecules, then I would use this factor. It's a Greek letter epsilon. It's 8.85 times 10 to the negative 12. Let me hold off on the units for just a second. But this is the number that I would use if what I had between them is free space. But if I don't have free space, then that number is increased by some factor. And so we like to say that the capacitance is increased by a dielectric constant. How much more is the capacitance? Well, this might be a good time then to give you a new and very useful word for our units. Because remember I said that the capacitance for that big one was 2,200 microcoulombs per volt. Well, this unit a coulomb per volt is given a name. And so I told you we're going to see a lot of this. It starts with Newton. We saw it last semester, but not nearly as much as we're going to see it this semester. We named the units after these great scientists and on their field. So we had Newton, we had watts, we had joules, and so far we've had volts. But here is one after Faraday, and so it's called a farad, capital F. And so when I pick up this capacitor, it actually says on it 2,200 micro, and it's got a little F, microfarads. And so that fancy word, that farad, so 2,200 microfarads. That's really what it says. And so keep in mind then that a coulomb per volt is a farad. Just like we learned a little while ago, a joule per coulomb is a volt. And so those are our units in honor of, like I said, those great scientists working in that field. All right, so I want to show you that if I had a parallel plate and if I had nothing in between them, this would be its capacitance. Now, unless I make a vacuum, I can't really have nothing in between them. So I will say that I am making close, but not perfect, a free space capacitor right here. This is my capacitor. And so if I take a capacitance meter, and so as the name implies, a capacitance meter will read the capacitance. It'll actually then connect up here, so I will go plus and minus, and I will turn my dial to a very low setting because this is a very low capacitance. Maybe I'll just do that so you guys can see it. But from where you are, hopefully you can kind of see that it says 144. And my dial is actually set to read up to it says, can read up to a maximum of 200 picofarads. So in other words, my units are picofarads. And so maybe it's worth remembering or reminding you. I don't know if we've ever done pico yet, but that one says my capacitance is 144 picofarads. Anybody know the prefix for pico?
10 to the minus 12.
Yeah, 10 to the minus 12, 1 trillionth. So this is 1.44 times 10 to the minus 12 farads. But I will say, a fair warning to all of you, you might need to go back to chapter 1 a lot in this chapter because we've got these prefixes that we haven't used a lot. Nano, micro, pico, and the list goes on. Okay, and so this, like I said, is a small one, picofarads. But let me change what I have between here. Now, I guess I will start by, actually maybe I better start by leaving it on and just go to the next dial setting because we're going to get bigger and we'll go over the 200 picofarads. And so I should have started here. So this one reads in nanofarads. And so it says 0.143. And so other than a small difference here, I've got 0.143 nanofarads. Now remember, nano is 10 to the minus 9. So these are the same thing, right? This is just moving the decimal 3 that way, and so this becomes 3 times bigger. All right, so it's same capacitance, same reading, but on a scale that reads in the nano of farads. Because I want to show you then, if I take this capacitor then apart and fill it up, the whole space. So notice by the way, the spacing is still the same. The area is still the same. So I'm not changing the area of the plate. I'm not changing the distance between them. That's why I made these spacers out of the same piece of vinyl. I just cut it off that piece of vinyl and said, okay, let's make sure what I'm changing is right here. I'm changing the material that's between the plates. I'm adding an extra piece here. In fact, your author gives a good picture of the physics behind this. He says, let's take a look at what might be happening on the inside. And he says, if you have a positive and a negative, and of course there's nothing there, you just get an electric field. But then if you put some material between this, and so in my case vinyl, what's going to happen is the molecule's going to get stretched, and the negative pieces get pulled over towards the positive, and the positive part of the molecule gets pulled over towards the negative, and so you get this kind of these elongated stacks of plus minus, and then down here he said, well, that's kind of the equivalent of one big piece where this edge has a bunch of negatives and this edge has a bunch of positives. And so, now he doesn't show the electric field before, but the electric field before we put the material would be these lines, all of them going straight across. And then he makes this argument here that some of these lines are going to terminate because there is an effect of a little bit of negative charge. Now, not all of them will terminate. So he's not trying to say that the negative here is exactly equal to the positive. Otherwise, all the lines would stop. He's just saying some of them do. And so he's drawn it so every other one is stopped, and so only half of them continue on through. But of course, now remember, the other side is the equivalent of being positive, so they get restarted again, and they continue on, and which is important because we'd have the same negatives over here, so we've got to terminate the same number of blue lines over here that we originally generated here. But in the material itself, the electric field is smaller. Now remember, capacitance is the amount of charge per volt. And remember, the voltage is the summation of the strength of that electric field. So if you put something in here that lowers the strength of the electric field, you're going to get now less voltage. And since the capacitance is charge per volt, you got a smaller number down there, less voltage. And so you're going to get a bigger capacitance. You're going to get a bigger capacitance by however much you reduce that field. This picture kind of shows a factor of 2. So I would say that this picture is illustrating that the capacitance would go up by a factor of 2. Now I know from experience that the vinyl is much bigger than a factor of 2. We'll measure it right now. I think it's around a factor of 5. But I think this vinyl reduces it by like a 5-to-1 ratio. So let me see if I can center this up pretty good and say, what is my capacitance now? And so now, well, that's not going to be a 5. Well, let's do the number here. Maybe I'm remembering paper. Well, anyways, but let's just see what we get here. But it looks like my capacitance now is 0.471 nanofarads. And so remember, it was 143 and it went up now to 471. And so it is this extra factor. It is this, what we call the dielectric constant, the material in there that added to it. Now again, like D, there's good and bad about putting material in there. You put material in there, you can get a higher capacitance. That's probably good. What's bad is now you give an easier path for the sparks to occur. And so you put material there that can actually break apart. I mean, at least if we didn't have material there, we could probably build up the voltage higher. Now we got to go lower, but we get more capacitance. So what's the trade-off? Is it worth putting the material in there or not? And so, like I said, it depends what you're after. But you can see then that if this is the capacitance then when we put the material in, and this was the capacitance without the material, what we call free space. And technically, like I said, technically it's not free space. Huh? Oh, I never came back to the units. Thank you for reminding me that. Yeah, let me get the, yeah, I'm going to come back to that. Thank you. But let me get this dielectric constant here. And so I would say take this 0.471 and divide it by 0.143 nanofarads. And this is going to tell me my dielectric constant. How much bigger did it get? So 0.471, 0.143, and looks like 3.3. So my dielectric constant for my vinyl, it's actually kind of a dual vinyl, two different types meshed together, comes out to be 3.3. And so the good thing about this piece of vinyl is I can get bigger capacitance. Bad thing is now I give a place for, as you saw, the sparks and all this stuff to explode on me. Yeah.
So why does like adding the material in between attract more charge in the plate?
Oh no, it's more charge per volt.
Or I'm just reading his description.
Oh, okay. Well, so his description is saying this, that why don't I make a little clear spot right here? If it depends. Actually, I'll draw both. It depends how it's hooked up, because if you take capacitor 1 and you hook it to a battery, so plus minus, and let's just say this battery is 12 volts, you're going to get a bunch of positive, because lack of electrons will come off, and negative. And that's going to make then an electric field. And so the electric field will look like this. And then if you put some material in between, it's going to get polarized and terminate, and I'll just kind of get rid of 2 of them, like that. And so that means the electric field here is not as strong as it used to be, but it needs to be 12 volts, so what's going to happen is the battery is going to send out more charges and suck in more charges, which then generates like that. And so eventually, through the material, we end up still getting our 5 lines that I originally had. And so it puts more on the plate. I think that was your question. Is that what he said here? It draws more out? And I would say it draws more out because we are connected to a fixed voltage supply. Let me change the situation, so we can do kind of a comparison and contrast. It'll probably make more sense then if you then say, what if we did this? What if we then first hooked it up and then disconnected it? So we put a plus and then we put a minus. So I'll do this. I'll say, well, you're going to hook it up. And so now I get a plus and a minus. That gives me my electric field, 5 lines, 1, 2, 3, 4, 5. And if I were to disconnect, I get a little different scenario. This is based on that principle of conservation of charge, right? You cannot increase the amount of charge on its own. You can't just make electrons out of nothing. They got to come from somewhere. So in this first scenario, to keep the voltage up to 12, it put more out there. And it can do that because there's lots of charge inside of this chemical. But if you disconnect it, it can't do that. And so what happens in this case is you literally get then a termination of some of the electric field lines, and you actually now get lower voltage. So here I would say, once I put that material in there, it lowered from 12 volts down to maybe 8 volts or some value. And so it's real important that you understand what's going on in addition to the plate and the dielectric, but how is it connected? And so that's the two scenarios that I think need to be compared here. And in his example, he's doing this one, and that's why he said more charge will go on. But I didn't want you to mix it with this scenario too. Yeah. And so that's that great subtlety. All right, so now let me go back to the units here. I said I would come back and tell you then the units, but I think you can begin to see it. Since capacitance then is going to be measured in farads, let me clean off a little space here. The units for this permeability of free space then would be a farad, because that's what we ultimately want it to come out to be. This is capacitance in farads. And then if you look at this other stuff, this is a square meter over a meter. So that means you got a meter upstairs. So farad per meter would be the units. So that I can then go a meter, those would all cancel, and then that would come out into farads. And so that's important that, again, we're in our base units. We need to do distance and area in meters and square meters, and we will get our capacitance then in farads. And you can again see this is a small number. That's why our capacitance usually come out to be pretty small. You saw the numbers I'm working with here. These are nanofarads. And in free space it was in picofarads. So, and even these fancy ones are still microfarads. Now, there are thousands of microfarads, so you might want to call them millifarads. But it's rare to get something as big as 1 farad. But this one is. This is actually 1 whole farad. This is the one I said that it's got a surprisingly large surface area if you were to unwrap this thing. It's amazing how long it is. But again, really tight together. So it's really carefully manufactured so they don't touch them, and you can only get 5 volts on it because, again, you'll get sparks and you'll get this thing happening. And so that's the trade-off with all of this. Well, let me show you then a table, because you'll need this for different problems. Your author has this nice table here that says, what is this dielectric strength here? And so notice then that at the beginning he says a vacuum would be 0, and that kind of makes sense. That would be this first statement. This is the capacitance for a parallel plate. You would just put a 1 right there. And then all the other things would be something slightly greater or even much greater than 1. And well, here's my nylon, which is pretty close to my vinyl, and it seems to match there. So I got 3.3, and that's 3.4. I don't think they have vinyl in here, but I'll take it as nylon, and it's a good match. 5. Maybe I was thinking of glass, because the Pyrex glass here is 5.6, but for some reason I had a 5 in my head. Anyways, and that's our table here for our dielectric. Now, here's where it can get even more interesting. Let's see if I can just get both of these on here. What if we have more than 1 capacitor hooked up? What if we hook it something like this, where we have our battery, and then we take the wire, I'll go from the negative, and we go to the first capacitor, which then goes to the second capacitor, which then goes to the third capacitor, and then back. Well, let's come back to that picture, but I want to point out that we could have a different picture. We could have this. What if we have a wire that comes out of the battery and goes to each of the capacitors, kind of each of them separately, so it can go one or to the other? Ooh, what would happen here? How would these capacitors behave? Well, let's give a name here. We call this connection parallel, and we call this connection series. And if we step back and think a little bit about the name, or I should say the wiring, hopefully the name will make sense to you. I mean, here's what this is saying. You're saying that an electron would come out of here, go onto this plate, and then get stuck there. Because remember, there's an insulator between there. The electron can't go to the other plate. However, what the electron can do is, with its electric field, push an electron, a different electron, off the other plate. So electron number 1 is going to come out of here and go on this plate. It's going to create an electric field which pushes an electron off of here, and that electron goes from what I'll call capacitor 1 into capacitor 2. And of course, meanwhile, now we've got a plus and minus charge on capacitor 1, and the electron has gone into capacitor number 2. And then the same thing happens. The electron that goes into capacitor number 2 gets stuck on this plate, but by its electric field, it pushes off an electron and making this one a positive plate here. And this electron from capacitor number 2 goes up to number 3. So you see how we have a series of events? Do you see how we have a series of connections? It's kind of like physics here. You got to take physics 110 before you can get into 111. It's a sequence, and you can't really do 111 well without doing 110, right? We've already talked about the principle of conservation of energy and adding vectors together. We got to use those resources, and so we call this a series because it goes one into another into another. In your case here, you start off at certain classes, lower division classes, because you need those to understand your upper division. And so you got a series of classes you have to take before you have enough knowledge to graduate. And, eventually you'll get your bachelor's, but you're going to start here at a community college and then transfer to a four-year school somewhere. Okay, so it's a series. And that's exactly what this is. So let's call this series, as opposed to this kind of connection. Let's call this kind of connection a parallel. Because again, if you think about what's going to happen here, is the electron, the first one's going to come out here, go down and go, I could go here, but I could also go here, or I could go here. I've got options. I've got these parallel directions I could go. The second electron, let's say the first one, picks this one. So the second one might come up here and go, no, I don't think I'll go that direction because there's already somebody there. They're negative, I'm negative, don't really like each other. I'll move over to this next one. And the third one does the same thing and goes here. And so we've got 3 electrons. They go to different places. Each of them chase an electron off of them and bring them back. And notice then we've got the complete circuit, if you'll let me say that word now. But they didn't go through all 3 of them. Each electron only had an influence on one of them. These are parallel paths. You don't go all of them, you only go one. It's kind of like a freeway. You get on the freeway, there's 3 lanes. Pick a lane and go. You get to CARP by one of those lanes. But you don't have to go all 3 lanes. You don't have to go here down to CARP, come back, and go back again to get to CARP. You don't have to go to all the 3 lanes. It's not a series. It's one or the other. It's parallel. Or you could do this. You could say, I'm going to take the freeway, or I'm going to take Foothill. And I'm going to go Highway 192 the whole way to Carp. Probably a bad choice, but you could, right? It's an alternative path. It's a pathway. You could take classes here at City College, but you could also drive down to Ventura and take the same classes, but you don't do both. You don't take classes here and then go to Ventura to take them, and then up to Allen Hancock and take them, right? It's one or the other. It's parallel. They don't feed off each other. You could take this class and your biology class. Now, in summer school you couldn't. That'd be too much work. But you get the idea that during a regular semester, you could be in parallel paths. So let's call this parallel paths. So this is called parallel, and the other one is called series. And if you take a bunch of capacitors and you hook them up, and your author there has 3 of them, and you hook these 3 capacitors together, your author is trying to say that that's equivalent to 1. It's equivalent to one giant one. And he's trying to say that giant capacitor, and so he goes C sub P is equal to the sum of the 3. You can kind of see it this way here. Watch this. What if I were to say the total capacitance would be nothing more than the total area over the separational distance. See, I'm hoping you can kind of see that really these 3 are functioning independent of the other ones. They're just storing up charge. And you could get the same effect if you just stacked them all together and had one big plate, where the one big plate is equal to the sum of the individual ones. And so I would say that right here, the total area is equal to the area of plate number 1, area of plate number 2, area to plate number 3. And now if we separate out using some little algebra here, you will see exactly what your author derives, which is to say that you can either think of this as one giant capacitor or 3 individual capacitors, because these individual ones, capacitor 1, capacitor 2, and capacitor 3, all add up to the equivalent one. And so these 3 add up. And make sure I don't run out of time, if you let me maybe hook this up, I have somewhere, 3 capacitors right here. And if I measure these capacitors, and these are in the microfarads, and maybe in the interest of time, maybe I'll only do 2 of them. But this says that this big one right here is 0.982. .982 microfarads. So that's my first capacitor. Let me then hook it to my second capacitor, which it looks like it is 0.457 microfarads. And like I said, in the interest of time, well, I could probably make it. Should I do a third one? Sure, why not? Yeah. Gonna throw me off here. All right, because that one's really small compared to the other ones. All right, but what I'm saying is if I hook them in parallel, I just add them together. And so let me do the math and saying, all right, if they're in parallel, I will add them. So a 2 and a 7 make a 9, an 8 and a 5 will make a 13, carry 1, that's a 14. And so if they're hooked in parallel, the equivalent of those two should be 1.439. Okay? And so where I want to spend the time is, well, series also, but showing you here that, okay, how do I hook these up in parallel? And that's a little bit of a little trick here. So let's see. If I understood this right, parallel would mean that two plates, and so that looks like the negative one, and traditionally we use black for negative, so I will follow that same suit here. Okay, and so I will hook the black ones together. Okay, and then I will also hook the red ones together. And so I would say they're in parallel. I have just connected the two top plates, that's the red wire right here, and the two bottom plates, this is the black one. So I guess it looks kind of like that. And they are now in parallel. So I'll come over here and I'll hook it to my meter to take a reading here. And so my meter says the equivalent capacitance of the two of these together is 1.439. Oh, exactly on. Okay. And so it matched. No, even uncertain. My partner this time was pretty good. All right. My partner didn't mess up. And so that's this equivalent. Now, the harder one is the series. And I say harder to understand, but actually much easier to hook up. And so let's take a look at this picture again. Your author is saying, okay, what would be the equivalent of these three? And I'll just hook up the two. But whether it's 2 or 3 or 4 or 5 or 6, hopefully you see the pattern here. And he does this. He says, well, what you could do is you could really say that these three actually all have the same area. In other words, they're equivalent to this, where these three, just this total distance right here, is the sum of the distances between 1, 2, and 3. So I would write it this way. I would say that the capacitance in series would be epsilon naught times the area over D total, where D total is the distance between capacitor 1 and capacitor 2 and capacitor 3. And so we have the same kind of idea that we did for parallel, but unfortunately the summation of the three is in the denominator, and that makes the math harder because you can't just separate them apart like you can do in a numerator, because then they would all have a common denominator, and so you can't just break it apart. However, we can do this. Here's some tricky math. Let me go ahead and take the reciprocal. Because as I just said, what was bothering me was the fact that those addition was in the denominator. So the best way to answer it is get it out of the denominator. Take the reciprocal of it. And so what you're going to have then is a common denominator of epsilon times the area. And now you can separate the summation like we did for the parallel case. But of course, remember that over here we don't have the capacitance, we have the reciprocal of the capacitance. But actually it's kind of nice, because what's this? Isn't this the reciprocal of the capacitance of number 1? I mean, if you turn that upside down, I would say that's the capacitance of number 1. So this is 1 over capacitor 1, this is 1 over capacitor 2, and this is 1 over capacitor 3. And so this one is different, and I have erased it, but when they were in parallel, you just added them together. And we did, and that was the easy one. That's why I wanted to do it first. The series is a little bit harder because what you have to do is take the reciprocal of each one, add them together, and then of course that is the reciprocal, so the last step is to take the reciprocal of all that. I like to write it this way, that the reciprocal of the series is the reciprocal of number 1 plus the reciprocal of number 2 plus the reciprocal of number 3. And so I want to show you a little trick that I like to use on my calculator to make these much easier. And on my calculator I have, and I'm sure yours does too, but which model do I have today? A TI-84, but there's a little reciprocal button right here. And so if I wanted to do this calculation and say, what is this the reciprocal of? I would just do this. I would take my first one right here and go 0.982, and so 982, and then I'd hit the reciprocal button. So then I go here, reciprocal, and then add. And then I'll take the second one, 0.457, and hit the reciprocal button, reciprocal. And so I just have entered the reciprocal of 1 and the reciprocal of 2. And then I'll hit enter. So I've just added them together. Now, what that has given me is not quite, I'm not quite done. What it has given me is the reciprocal of the answer. So, one last time, I hit the reciprocal button again and hit enter. And so when I do all that math, I get the capacitance of series at 0.312 microfarads. And so that would be the equivalent of 2 in series. Let's hook it up. All right, so let me show you this again. I'll leave the meter off to the side. But if I go to hook this up, like I said, this one's a little bit easier to kind of recognize. I guess I would say, well, one wire would come out and go to my first capacitor. So let me call this the first capacitor. So right here, this wire here is going to be that one. Then it goes up to this wire right here. Okay, so I'll put a connection right there. Okay, so it goes from here up to there. Then this wire is supposed to go to capacitor number 2, so why don't I just connect it right there? Okay, so this wire has connected here to here. It has connected the top one of number 1 to the bottom of number 2. And then this right here would be that one. And so I would like to know what is the capacitance between here and here, because this has just connected them in series. So I guess I don't need that wire. I just needed one to connect right there. And then I can come over to my meter and connect it here and here. So I'll come over here and I'll take my capacitance meter and I'll put one on the top plate and one on the bottom plate, and I will get a capacitance of 0.312, 0.312. And so that's the equivalent when you hook them all together. All right, well, our timing worked out well. It's our quitting time. I think it's the first time we're actually done at quitting time, and get out of here before the next one starts. And I'll send you some problem solving supplements ones, and I'll also do a video of your question about, I forget which number it was, but back on chapter 18, I'll work that one out. Send that out to everybody. All right, take care. You two online. Bye now.